Yes. The next one is the Laplace equation, which is denoted by del square u equals to 0. This del square, we call it as a Laplace operator, just now we discussed, and which is denoted by this symbol. And in mathematics and physics, Laplace equation is a second order PDE named after Pierre Simon Laplace. And this person, Laplace, is a French scholar and a polymath. Polymath means he is expert in many fields of mathematics. And his work was very important to the development of engineering, mathematics, statistics, physics, astronomy, and philosophy. Laplace formulated Laplace equation. He pioneered the Laplace transforms, which appeared in many branches of mathematical physics. So these are the some information about this Laplace, and this equation which he derived is known as Laplace equation, and it has variety of applications, and you can visit Wikipedia and just see what are the informations available under Laplace transform. So what is a Laplace equation and who derived it? So, and this graph, you can see this is a solution of a Laplace equation. You can just see this is how the solution is. And now we go to the next equation. We call it as Helmholtz equation. Helmholtz equation. In mathematics, the eigenvalue problem for a Laplace operator, we call it as a Helmholtz equation, and it corresponds to the following PDE called as del square f equals to minus k square f. And del square is known as a Laplace operator or a Laplacian. K square is the eigenvalue and f is a eigenfunction. When this equation is applied to waves, this k is known as a wave number. So we have a lot of other informations when you apply for waves. This Helmholtz equation has a variety of applications in physics, including wave equation and the diffusion equation. It has many uses in other sciences, and it is derived by, this equation was derived by Helmholtz, and he is a German physicist and a physician. Physicist is a person who is expert in physics and who also made a significant contribution in several scientific fields. And this is called as a Helmholtz operator. Sorry, Helmholtz partial differential equation. Next one is Navier-Stokes equation. Navier-Stokes equation. And that equation is denoted by dou u by dou t plus u dot, and it's a vector equation. That is why we call it as set of, a Navier equation is a set of PD. We call it as del u equals to minus del t by rho plus nu into del square u, where u is the fluid velocity vector, and this P denotes fluid pressure, and this rho denotes fluid density, and this nu denotes kinematic viscosity. And this del square is already known. It's called as a Laplacian or a Laplace operator. You can simply write Laplacian. And what you can see is this Navier-Stokes equation is a set of PDEs which describe the motion of a viscous fluids. It is a set of partial differential equations which describe the motion of a viscous fluids. Describe the motion of viscous fluids And this equation was named after the French engineer and a physicist. We call it as Claude Louis Navier. Claude Louis, just wait, I'll change the spelling, L-O-U-I. Louis Navier, and two persons derived this Navier-Stokes equation. George Gabriel Stokes. Derived Navier-Stokes partial differential equation. And this Claude Louis Navier is a French engineer and a physicist, and this George Gabriel Stokes is a mathematician. See, these both derived this Navier-Stokes equation, which is a set of all PDEs which describe what? The motion of a viscous fluids and substances. So this is application of this PDE. So what is happens? This monitors this describe the motion of a viscous fluid, this PDE, and if you find the solution of this PDE, we get U. U is nothing but the fluid velocity vector. So this is Navier-Stokes equation. And I'll just give you some graphs. And the next, the final one we are going to discuss is called as a wave equation. And it is an important, wave equation is an important second order partial differential equation for the description of waves. So now I am going to write what is wave equation. Fifth one. There are many differential equations which has variety of applications. We are discussing only very few. The wave equation is an important second order linear PDE. Wave equation is an important second order linear PDE important second order linear partial differential equation for description of the waves. Description of waves. And we have going to now see what is the one-dimensional wave equation. Dou square u by dou t square It's called as one-dimensional wave equation. So one-dimensional wave equation. And this is the just you can visualize this is how the wave equation propagates, and the solution of this differential equation we get waves like this. This is one-dimensional standing wave as a superposition of two waves traveling in opposite directions. And there exists another wave equation, we call it as two-dimensional wave equation, that is also available, which this is a one-dimensional wave equation. The two-dimensional wave equation, we have one more term in that, like this: dou square u by dou t square equals to c square into dou square u by dou x square plus dou square u by dou y square. Two-dimensional is called as a two-dimensional wave equation, and this is how the wave propagates. And this c square is nothing but where c square is nothing but t by m. It's derived, and T is the tension of the string, and this M denotes the mass per unit length of the string. And it was derived, this equation was derived. And what is this U? If you solve this one-dimensional wave equation, suppose if we solve this, we get the function U, which is a function of x, y and t. Okay. Sorry, if you solve this one-dimensional wave equation, it is a function of x and t. Sorry. Okay. Suppose you just see a tightly stretched string tied at both ends A and B, and thus you give the velocity here in between, so the string starts move like this, transverse vibration. It just continuously moves. Suppose this is this way AB is this x-axis. Suppose I am at this point x. So what happens is, at the same point, so I am going to calculate what is this vertical displacement of the string. This vertical displacement is denoted by u of x comma t. This is, we call this as u axis, and this is okay, u of x comma t. But at the same distance x from A, at different time this vertical displacement will be changing. So we are going to solve this PDE and get that function u, which tells you the vertical displacement of the string at any time t at the point x distance from the initial point. So these things all we are going to study very detailed in the final units. Okay. So this is a one-dimensional wave and heat equations. And the problem of vibrating strings, that's what we are going to study very deep. Vibrating strings such as a musical instrument was first studied by D'Alembert, Euler, Bernoulli and Lagrange. These are the four persons who started investigating about the vibrating string such as the musical instruments. But D'Alembert discovered the one-dimensional wave equation. The D'Alembert, D-A-L-E-M-B-E-R-T. And within 10 years, Euler discovered the three-dimensional wave equations. So, wave equation mainly found by D'Alembert and Euler. D'Alembert derived two-dimensional wave equation. Sorry, he derived one-dimensional wave equation, but after 10 years, Euler discovered three-dimensional wave equation. So this D'Alembert derived one-dimensional wave equation and Euler derived three-dimensional wave equation. After a 10 years gap, after this D'Alembert derived this equation, one-dimensional wave equation, this which was given here. This is one-dimensional wave equation. This is derived by D'Alembert. After that, Euler derived a three-dimensional wave equation. Three-dimensional wave equation means c square into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. One more term will be inside that. So this is the details about wave equation. Now, for our study, already I have just indicated, for our study, we restrict to PDEs, involving one dependent variable, say Z, and only two independent variables, say X and Y. Here always Z is my dependent variable, which is a function of two independent variables X and Y, and we use the following notations always. Small p denotes dou Z by dou X, already I have included. Q is dou Z by dou Y, R is dou square Z by dou X square, S is dou square Z by dou X dou Y, and T is denoted by dou square Z by dou Y square. And now we are going to see how to derive a PDE. Derivation of a partial differential equation from a given solution. The solution is given. Now we are going to find what is the corresponding PDE. There are two things we are going to do. First, we are going to derive a PDE by eliminating arbitrary constants from the relation between x and y. And second thing is eliminating arbitrary functions. Formation of a PDE by eliminating arbitrary constants and formation of a PDE by eliminating arbitrary functions. Arbitrary means its values are not determined, it's not assigned specific values. So we call it as an arbitrary constant, arbitrary functions. Now one by one we are going to discuss the method how we are going to derive a PDE. Usually a PDE is given, a partial differential equation, suppose a wave equation. We try to find the solution. That is what we are going to discuss in the final applications of partial differential equation. But here the solution is given, the function u is given. We are going to see from where this PDE, this function was derived. What is the PDE to which this function is a solution? So this is what we are going to study here. So now the first topic is formation of a PDE by eliminating arbitrary constants. Formation of a partial differential equation by eliminating arbitrary constants. We are going to see this. First we are going to learn the method, then we will go for the problems. Now let us consider a function that is a solution of the PDE. Consider a function f which is depending on x, y, z, a and b. I name this function as 1. Here this x and y is actually, as already said, this is x and y are two independent variables, and z is an dependent variable. Here this a and b are called as arbitrary constants, and now we are going to eliminate this arbitrary constant and derive that PDE. So the concept is to eliminate two constants from the above equation. To eliminate two constants, we require three equations. To eliminate two constants, we require three equations. Now we are going to form that another two equations. Now differentiating this first equation partially with respect to x and y, we get, first you take the first equation and differentiate partially with respect to x. So dou f by dou x, right hand side is 0, so if you differentiate again it becomes 0. That is, but my f is a function of how many variables? X, Y, Z, A and B. This f depends on X, Y, Z as well as A and B also. But now, so if you differentiate what is dou f by dou x, and f is a function of this much variables and constants. So what happens is, this dou f by dou x we are going to write like this. This is taken from total differentiation. This is called total differentiation. That is, first we are going to one by one. First we are going to differentiate with respect to this x, and this x again we are going to differentiate with respect to x, and the other thing is now y. So this f we are going to differentiate partially with respect to y, and this y we are going to differentiate partially with respect to x. Next is z. This f you differentiate with respect to z, and this z you differentiate with respect to x. And next is a and b. So f you differentiate with respect to a, and this a you differentiate partially with respect to x. This is called total differentiation. And next, dou f by dou b into dou b by dou x, and the right hand side is 0. This dou f by dou x is written like this. But a and b are constants, they don't depend on x, so these two terms will become 0. It is, so what is this? This becomes 1, so this is written as dou f by dou x plus, and x and y are independent variables. So if you differentiate y with respect to x, this also vanishes. Now dou f by dou z, and what is dou z by dou x? Already I know, we told this is p. This is my second equation. That is, we differentiated one partially with respect to x. Now the same way you differentiate one partially with respect to y. If you differentiate one with partial with respect to y, we get dou f by dou y equals to 0. So same like this you do for this one also. So what are the variables this f depends? X, y, z, a, b. In that order you can go. So this is, first you differentiate with respect to x. F with respect to x, and this x you differentiate with respect to y, plus dou f by dou y, and y again differentiate with respect to y. This becomes 1, plus dou f by dou z into dou z by dou y, plus dou f by dou a into dou a by dou y, plus dou f by dou b into dou b by dou y equals to 0. Same like the previous step, these two things vanishes because a and b are constant, and x is independent of y, so this also becomes 0. So we get, it is, this becomes 1, and so dou f by dou y plus, and this is q times dou f by dou z equals to 0. This is the second equation. Sorry, this is a third equation. So what is the procedure is, eliminating a comma b from this first equation, second equation, and third equation, we get a partial differential equation of the first order of the form. I'm just denoting that partial differential by capital F. That depends on x, okay, y is there, but a and b is eliminated. In place of a and b, it depends on p and q. So since p and q is involved, that is called as a partial differential equation. This is the required partial differential equation. This is the method. Now we will see the problems. Now we are going to deal with some problems. First problem, eliminate a and b from z equals to x plus a into y plus b and form a partial differential equation. This is the question. We are going to use the method described above. Now let the given function, I name it as 1, x plus a into y plus b. Actually this is the solution and we are going to find the corresponding partial differential equation. But in the application of PDE, the partial differential equation will be given, but we will be finding the solution later on. Now this function is given, I name this as 1. As per the method I go. Now what we do is simply you differentiate just a minute. You just simply differentiating 1 partially with respect to x and y we get. So first you differentiate 1 with respect to x, so what happens? Dou z by dou x equals to, you differentiate with respect to x, I get y plus b, and this is nothing but p, and this equation I name it as 2, and differentiate with respect to y, what I get? Dou z by dou y equals to x plus a, that is nothing but q. Now I got 3 equations. My aim is you have to eliminate a and b from these 3 equations. So what is the available technique is, this p is y plus b, q is x plus a. You substitute these two in 1, so a and b are eliminated. Therefore the method thing is using 2 and 3 in 1, we get z equals to pq. That's all. This is a partial differential equation because it involves partial derivatives p and q. So this is the required partial differential equation and the problem is done. This is the simplest problem and this is a method. So not always you will be using substituting 2 and 3 in 1. From these 3 equations, our aim must be to eliminate that a and b, and the resulting equation must be the PDE, required PDE. Not always that we have to substitute 2 and 3 in 1 and get it. Not always. Sometimes we may not use 1. We will use 2 and 3 and eliminate it. So the second problem. Question is, obtain the partial differential equation of all spheres whose centers lies on the plane z equal to 0 and whose radius is constant, and that constant is equal to r. They given that the constant of all the spheres whose centers lies on the plane z equal to 0 is r. So what is the general equation of a sphere with center ABC? You write like this: x minus a the whole square. Wait, I will write it. General equation of a sphere of center ABC and radius r is given by x minus a the whole square plus y minus b the whole square plus z minus c the whole square equal to r square. Okay. The center is ABC, but we are not going to discuss only one sphere. All spheres lying on the plane z equal to 0. Plane z equal to 0 means that is nothing but xy plane. On the xy plane, all the spheres, the center is on the xy plane. So for all those spheres, the value of C is 0. So, but here the C is 0 and A and B are arbitrary constants. Arbitrary constant means the value is not assigned. So this is a family of spheres. A and B is not a constant. We call it as an arbitrary constant. The meaning is there are many spheres in it. If you change A and B alone, we get another sphere. But all the spheres with the C equal to 0 will lie on the centers will all lie on the xy plane, that is z equal to 0. So what we are going to do is, this is the sphere equation given. So what is the corresponding partial differential equation we are going to find. So for this problem, my sphere equation is x minus a the whole square plus y minus b the whole square plus z square equal to r square. Here r is a constant they given. All the spheres they have the same radius r, but their centers are lying on the xy plane. That is are changing. Okay, so a and b are, we call it as arbitrary constant and r is a constant. So now this is my first equation. This is my first equation. Our aim is to remove this a and b. R is not an arbitrary constant, it is a constant. Okay, this first equation is a family of spheres. Many spheres are there. All the spheres have the same radius, but the centers are lying on xy plane. Okay, so differentiating the method, we are going to derive the partial differential equation now. Differentiating one partially with respect to a and respect to x and with respect to x and y, we get, so what happens, 2 into, first differentiate with respect to x partially, x minus a, 2 into x minus a, and if 2 into y minus b, and then you differentiate y with respect to x becomes 0. Why it becomes 0? Because x and y are independent variables. And what is the differentiation of z square with respect to x? 2z into dou z by dou x, all partial differentiation. And our r is a constant is given, so if you differentiate with respect to x becomes 0. So what we get, x minus a plus 2z into p equal to 0. Similarly, if you differentiate with respect to y, what happens? 2 into y minus b plus 2z into dou z by dou y equal to 0. It is y minus b plus zq equal to 0. I name this as equation 2, and this is equation number 3. We got 3 equations, and now we are going to eliminate a and b. So what we are going to do is, using 2 and 3 in 1, what we get, how to eliminate it. So this x minus a is nothing but what, this 2 is not there now. So x minus a is nothing but minus zp, y minus b is nothing but minus zq. So what happens is, we substitute in the first equation. So minus zp the whole square plus minus zq the whole square plus z square equals to r square. It is z square into p square plus q square plus 1 equals to r square is the required partial differential equation. And we are done with the problem. So we go to the next page, and this is problem number 3. Find the partial differential equation of all spheres whose centers lie on the z-axis. Whose centers lies on the z-axis. So what is this set of all spheres whose centers lies on the z-axis? X, the coordinates of all the spheres, the x coordinate and y coordinate, the center x and y will be 0. That is the thing. And what would be that family of all the spheres? X minus 0 the whole square plus y minus 0 the whole square plus z minus c the whole square equals to r square. Here they did not tell that all the spheres have constant radius. No. So here they ask you to find the PDE of all spheres whose centers lies on z-axis. Simply, centers lies on z-axis. That is the only restriction. Centers lies on z-axis means it will be like this: x square plus y square plus z minus c the whole square, and radius may be changing also. That is why for this problem c and r both are arbitrary constants. This is the equation of all spheres with centers on z-axis. Here C and R are arbitrary constants which need to be eliminated. That's why we write the word arbitrary constant. I name this equation as 1, and we are going to differentiate 1 partially with respect to x and y we get. So what happens with respect to x? 2x plus, if you differentiate with respect to y, it will become 0. So 2 into z minus c into dou z by dou x equal to 0, because r is dou r by dou x is 0. So what we get is x plus z minus c into p equals to 0. I name this equation as 2. Similarly, what I get, if I differentiate with respect to y, I get y plus z minus c into q will be 0. This is third equation. Now, and here for this problem we are not going to use first equation. Simply we will complete the problem by using second and third. Therefore, from 2 what do we get? What is z minus c from 2? Z minus c is nothing but minus of x by p. And from 3 what I get? Same, z minus c is nothing but minus y by q. Since both of the left hand sides are equal, right hand sides also must be equal. Therefore, from 2 and 3 we get, from 2 and 3 we get minus x by p equals to minus y by q, which implies qx is equals to py, or qx minus py equal to 0 is the required partial differential equation. So see here, for this problem we have not used the first equation. So according to each problem we have to think how to eliminate those arbitrary constants. Now, very important thing, that's a note to keep in mind. If the number of constants to be eliminated, if the number of constants to be eliminated, if the number of constants to be eliminated is equal to the number of independent variables, an equation of first order PDE results. If the number of constants to be eliminated, is greater than the number of independent variables, the equation of the second and higher orders are obtained.